choose the other composition, that is totally insulated material. So there is a band gap in the bulk state, as shown in this figure. But interestingly, in this state, the Zeeman energy is twice as large as the cyclotron energy. So application field along the z-axis can close the gap. Then eventually it causes semiconductor to semimetal transition at a certain field. Then the experiments done in more than 40 years ago showed this kind of magnetic transport measurement. So resistance drops at around 10 Tesla. Then those also classified that as a semiconductor to semimetal transition field. Those guys left their sample in the underground area of our institute. Then I do the similar experiment in the extended field and temperature range. We can reproduce this negative resistance up to here, but above that we observe balance of second insulating state at around 20 Tesla. So with watching this data, I wonder whether this is really semiconductor to semimetal transition or not. To make clear that point, we performed ultrasound measurement. This field shows the field dependence of elastic constant. The elastic constant of this class of conducting material is described as this formula. And the second term contains the density of state at the Fermi energy as coefficient. So the emergence of band overlap causes this negative term. So the peak structure at around 11 Tesla means that band overlap appears about 11 Tesla. So actually the semiconductor to semimetal transition is actually appears at 11 Tesla. So our experiments showed that the band touching is overlap. So increase in the magnetic field only simply increase the density of hole and electron carriers. So there is no reason why to make the system insulating. So the single particle picture cannot explain the emergence of the insulating state. Then let us think about the many-body effect. So as I told before, all theories predict the emergence of extrinsic states in such a boundary region. Then Fenton predicted that such kind of state can be realized in magnetic field because we can continuously tune the band diagram using magnetic field. And also, application of high magnetic field shrink the wave function of the carrier. That reduces the shielding effect. Then the effective binding energy between electron and holes increases as a function of magnetic field. Then let us check whether our insulating state can be extonic or not through the order estimation. So first let us estimate effective binding energy between holes and electrons. Similar to the electron-proton system, hydrogen ion system, we can introduce the effective building energy with this formula. In our case, because of large d-electric constant and small effective mass, the effective building energy is as small as 16 microelectron at 0 Q. But application of high magnetic field continuously increase the binding energy up to 20 times larger than that at 0 Q. It means at around 20 Tesla, we can have the binding energy of 0.3 millielectron. That is comparable to the order showed if we the semiconductor function, we may have similar insulating state in the quantum limit state in the semi-metallic region. To check it, we studied the magnetic resistance of about 4% substituted material. And according to the old papers, in the transverse magnetic resistance measurement, the authors claim that there is steep increase in the resistance that corresponds to the same metal to semiconductor function. But our recent experiment in the experiment field region shows that the increase in resistance drops down at higher field. It means this state is not semiconductor. So careful analysis of this Shibirkov-Rojas oscillation and also theoretical calculation shows that this state is not semiconductor. So this energy diagram shows that the system becomes quantum limit state above the field of 30 Tesla. Above that, we have 3 electron pockets with the lowest Lambda sulfur. Application of field up to 45 Tesla causes a dry up of 2 or 3 filling pockets. So this is kind of so-called bipolarization. But we still have electron hole pocket up to 60 Tesla, which remains semi-metallic. But even in this semi-metallic region, if we apply the current parallel to the field, it shows diverging increase in resistance. So, according to the previous calculation, the function to the semiconducting state may appear at around 90 Tesla. So we have finite band over, but even though we have this kind of diverging insulating behavior in this state. So at the moment we have no good answer to the origin of this state, but we confirm that we have some insulating state in the same metallic side of semiconductor semi-metal function. And this phenomenon is not unique to this our Bismuth system. If you look at recent papers carefully, you will see similar phenomena in graphite and also calciumidate and tantalum arsenide and also pressurized black phosphorus. So we believe that if we go deep into the quantum limit state, strong correlation effect causes some metal insulator transition by the many body effect. So let me conclude my talk. So we call the band tuning of Bismuth unstimulated system by magnetic field. And at the vicinity of the semi-metal and semiconductor transition, we can go deep into the quantum limit state in this semi-metal material. Then observe insulating behavior only in the longitudinal magnetic resistance. So origin is not clear. So it may be possible to see the extonic phase, but we cannot specify it. Anyway, we have the insulating state at the vicinity of in semi-metallic side of this transition. That is all. Thank you for your attention.
Now it's time for questions. Okay, maybe, well, oh, yeah.
So, Professor, very nice talk. So, this magnetic field dependent transport measurement. So, are there like bulk sample single crystals?
Yes.
Okay. So, so what is the typical dimension? Let's say when this rho ZZ was measured.
Dimension sample is about millimeter. And
I mean, in the Z, how big it will be?
dimension of the sample?
No, I'm saying this rho ZZ. That's basically out of plane, right?
Okay. So this red dotted curve represents the ratio between the sigma ZZ and sigma XX. It goes to about 200 around here.
Okay. So, no, I was just like, so this looks like a hall bar kind of geometry, right? A hall bar.
Or
No, they have hall bar, like a off diagonal and then diagonal measurement. I mean, components are being measured,
okay.
right?
I have the data just a moment. Whole resistance. We also measure the transverse magnetic resistance, the whole resistance. What that is.
Okay. So, and this is a like a pulse field or
Yes.
pulse field?
Yes. In pulse field we measure.
Okay. So, do you think magnetization will also give you some additional information to support these things?
Yes, I expected. So then we measure the magnetic radiation also, but we observe only the monotonic diamagnetic signal.
Okay.
We cannot find any otherwise.
Sure. And so, how stable are these materials? So, how like environmentally stable?
I think it was grown more than 40 years ago,
Okay.
but the experimental results are almost reproducible. So in that sense, I believe that it's very stable.
Okay. So, for example, bismuth and antimony both are kind of like environmentally, like atmospherically very volatile. If you just make a thin film or elementally, if you try to handle. So that's why I try to know basically whether like it is stable for long.
Yeah, it's
So
a very good idea, but unfortunately, when we make a thin film resource system, many people fail to observe quantum oscillation.
okay.
The quality of the sample becomes worse in case of thin films.
Okay. Okay. Thank you. Okay. So yeah, now I would like to request the chair to please hand over a token of appreciation. Okay.
Thank you very much.
Thank you very much.
So please take a photo.
Thank you.
Thank you very much.
Okay, so now we have last talk of this session, and the talk will be given by Professor Rahid Ranjar Shahi, and he's from Department of Physics, Central University of South Bihar, Gaya. Before his current role, he was an assistant professor at Motilal Nehru National Institute of Technology in Allahabad. He pursued his PhD in physics at Banaras Hindu University, and his exceptional academic and research contributions have earned him numerous awards, including prestigious Young Scientist Award and the Inspire Faculty Award. His research interests span a range of topics, including hydrogen storage materials, high entropy alloys, and carbon nanostructures, focusing on their properties and applications in energy storage and catalysis. And today, Dr. Shahi will be presenting his insights on the topic of magnetic properties. Sorry, kind of a bit hard to pronounce that material, but based on high entropy alloys. Okay, yeah. Thank you. We have 20 minutes talking, like roughly 5 minutes for questions.
Hello. Yeah. So, good morning. Okay. So, good morning. First of all, thanks to the chairman for nice introduction and organizers for providing opportunity to talk here. So, today I am going to talk about some a new type of material, that is a high entropy alloy. So these alloys are discovered in 2004, since these alloys having more than 5 different elements, and the composition of these individual elements are 5 to 35. So if we are going to take more than 5 elements with having that composition 5 to 35, we can define these material as a high entropy material, because the entropy in the sense that configurational entropy. So here whatever we are, the phase stabilization and all the things are occur only due to the configurational entropy. So with this, yes. So we all familiar about the conventional alloy. If we see the conventional alloy, the picture is somewhat like this. In the conventional alloy, there is one principal element and some minor element to enhance the property. However, if we talk about these, as I told, high entropy alloys, working properly. So if we talk about this high entropy alloy, as I told, there is more than 5 elements, more than 5 elements. The maximum configurational entropy for this system is going to be around greater than 1.5 R if we consider it 5 equiatomic system. So if we have these 5 elements, system. If we have these 5 elements with 20 equiatomic each, then we have configurational entropy greater than 1.5 R. and by Gibbs phase rule we can understand why the single phase is going to be formed, because as the configurational entropy is maximized at a particular temperature, the minimum Gibbs energy is going to be obtained. So with this we can find a single phase, and so the atomic arrangement is somewhat like this. You can find there is a n number of different size element decorated in a that crystalline manner. So as I told you, if we are going to increase the number of elements, the configuration entropy is increases. We can see this picture. If we are increasing the number of elements, the configuration entropy is going to be increased, and this increment is occur up to the 13th element. So we can synthesize. People have synthesized single phasic alloy by considering a 20 element. However, the configuration entropy are increasing up to the 13, and then after the saturation is going to occur. So we can synthesize. We can take maximum number of elements to synthesize this type of alloy. The benefit of this is what we can find for the conventional alloy we have only one or two principal elements. So in that case the properties are going to be limited. Here we have a great composition in space to optimize the property. So why these material having excellent property? So there are 4 different core effects that will be responsible for these type of property. We are knowing that, as I told, we have 5 or more than 5 different type of atoms. Since we know that whatever the lattice is going to be formed, that lattice is the having that contain a different type of atom. Since these are the different type of atoms, the local chemistry is somewhat totally different. Local interactions are different, as well as the structures are going to be deformed structure. So these materials naturally deform structure. Sometimes we are going to increase some external process to deform a structure in order to tune the property. In this case, we have naturally deformed structure, as well as so we can say like that these materials having different property, like due to the lattice distortion, high entropy effect, sluggish diffusion effect, and cocktail effect. Cocktail effect is nothing but this is a combined effect of different atoms present in a close proximity. So the chemistry and the physical and chemical property of materials are going to be changed drastically due to the presence of different type of material. Now come to the motivation why these materials are going to be beneficial for the magnetic property, because we are knowing the conventional soft magnet are going to form by using iron, cobalt, nickel, and these iron, cobalt, nickel, we are knowing that these iron, cobalt, nickel alloys are going to be conductor. So whenever we use this type of material, definitely there is some loss as a form of eddy current, and these losses are up to the 9% of total generated electricity. So if we synthesize such type of material, and due to the presence of multi-component system, there is a electron phonon and scattering is very high in this case. Due to that, there is a chance these material having very high resistivity as compared to the conventional magnet. So these are the, as I told you, major property of the high entropy alloys are going to govern by these 4 effects. So these 4 effects are also important for the magnetic property in some sense. You can say that if we have this high entropy effect, the formation of solid solution phase, these effects are going to stabilize single solid solution phase like FCC, BCC. And second, and we can also tune this FCC and BCC according to the composition. And the second thing is that if we talk about the sluggish diffusion effect, this sluggish diffusion effect are going to promote formation of these nanocrystalline grains. So these nanocrystalline grains are also going to be helpful for the optimizing the SC of that particular soft magnetic material. Sluggish diffusion and distortion effect, as I told, this distortion is going to enhance the mechanical property of the material, as well as you can say this cocktail effect is again going to respond for the other functional property along with the that magnetic property. So these are the work which we did from last, you can say 7-8 years. So we synthesized some particular PIFP-NI based system, and we optimize it for a particular composition of for this system for high saturation magnetization as a soft magnetic and high resistivity of that particular alloy. So there are certain criteria through which we can calculate what phase can be formed before selecting an alloy. So you can see there are certain thermodynamical phase formation rule. Based on that, we can predict what type of phase can be formed for a particular combination of the alloys. And with this, we can predict which combination is going to form formation of FCC or BCC phase are going to be occur. So today I'm going to I'm going to talk the mostly work of this Dr. Rajesh Kumar Mishra is my first PhD student. So right now he is in Berlin. So we started with by taking a composition PIFE and ICR. Why this combination? Because these particular system having get good mechanical property. One of the major problem with that conventional magnet is that there is a malleability. Mechanical property of these conventional magnets are also not good. So we can select such type of material with particular material having certain strength as well as malleability, as well as you can say good corrosion property. Along with that, we optimize this material for the maximum you can say magnetization as well as porosity. So this one is our initial result in which you can find the magnetization is very poor. This magnetization is up to the you can say only 25 or 40 mu per gram up to that. Then we try to optimize this particular material in regard to the proper composition of iron, cobalt and nickel, and we come to the conclusion with the proper this iron, cobalt and nickel, we synthesize a single FCC phase with a particular composition. That particular composition is going to be so magnetization up to the magnetization up to the you can say up to the 78 mu per gram. So we can conclude like that whatever that property of these material having, that one is sensitive to the composition, and these particular system having similar structure, but by the composition variation we can obtain highest value of the magnetization. As well as you can see the SC is also going to be sensitive to how we are process our material. So most of the material is going to synthesize through ball milling technique. We use mechanical alloying technique because mechanical alloying is going to be used for such type of system, beneficial for such type of system, because this one is a slow diffusion process. If we have we are using some RF or arc welding like technique, in that case the sudden heat is going to be generated, and that sudden heat may be responsible for the formation of different phases. There is a phase segregation type things are going to occur for the case of arc and RF welding. However, if we go with the ball milling, in slow diffusion process, there is a possibility of formation of only single phases are occurring. So you can see with again we are going to change this composition, and we optimize this material for the stoichiometry for considering the ferromagnetic, non-ferromagnetic element, variation of ferromagnetic, non-ferromagnetic element, and we come to the conclusion if we have a particular composition of this cobalt 35, chromium 5, iron 10 and nickel 30, this particular material having that magnetization up to the you can say 90 mu per gram and having a SC around 1 to 2 ostet. So with this we again started to play some you can say annealing effect. We checked different annealing effect, and in annealing we found that material having 88 mu per gram as well as having SC12, and all this parameter lie in the range of you can say soft magnetic material. Then further, in order to tune the magnetic property, we anneal this particular material at different temperature, and since there is a solid solution phase, there is some interesting phase transformation can be occur, and we found this particular at 500 degrees centigrade there is some additional you can see in this case there is some additional BCC phase, slight amount of this BCC phase is going to be formed at 500 degrees centigrade, and rest of the material is going to be stable with respect to the annealing temperature. This is another benefit of this particular material, that this particular material is stable up to the you can say 1300 to 1200 degrees centigrade. The formed phases are going to be stable. Only change may occur that there is some allotropic phases are formed. Since this is a solid solution, if we are heating at different temperature, there is a possibility of rearrangement of the atom, and by the rearrangement of atom, the local region some allotropic phases are formed. So that will be also beneficial for the you can say for the mechanical as well as for the magnetic property in some sense. So this one is the work we did different effect of different annealing effect, and we found some interesting results in regard to how the material is going to change phase as well as magnetic property with respect to the different annealing temperature. So these are the microstructures. You can find there is a clear-cut formation of fine nanocrystalline particles. These nanocrystalline particles are the clear redax picture shows that each and every particle having the similar stoichiometry, and that stoichiometry is going to be there is a 5 different elements. So further, in order to this, we also try to see what will happen if we are going to change the processing? As I told, the processing parameter is another important term that can be tuned the property. So we synthesize a similar composition by using RF melting technique. You can see if we go with this particular material through the mechanical alloying, there is a formation of BCC phase. However, if we go with this through that RF melting, in that case you can find there is a formation of that. In this case, there is a two B2 type phases are formed, as well as there is an FCC phase. So this is again clear that for this type of systems, flow diffusion technique is one of the important aspects. So actually we want to check what is the practical aspect of this material, because sometimes we are not able to use powder material for the application purpose. So we want to synthesize a bulk material by using a melting technique. So in that regard, we synthesize this material for the RF melting, and we found there is a different phases are going to be formed, and this particular material having excellent hardness also. You can see that from the you can see weaker hardness that we use. So this particular material, both the material we use, this one is a ball milling sample, and this one is a, definitely there is a, since the metal melting process is occurred, due to that hardness is very high for this system, as well as the magnetic property of both the system are more or less similar, although there is a formation of some secondary phases are there. So these are the clear microstructures of ball mill sample as well as the RF melting sample. So we can say like that, whatever we can tune this material in regard to the, there are many aspects through which we can tune this material. First is processing parameter, you can say synthesis parameter, processing parameter, selection of the different alloying element, as well as compositional variation gives you the very interesting results. So further, in order to enhance, in order to improve the corrosion as well as mechanical property of the system, we again try to replace certain part of titanium with the aluminium, because we are knowing that the malleability is one of the issue for the conventional material. So if we replace the titanium with aluminium, then the material is going to be more ductile and malleable with the substitution of this aluminium. And we found again some interesting result. These are the phases. You can find there is a precipitation of some additional. This BCC phase are going to occur when we use different type of with the different concentration of the aluminium, and this BCC phase concentration is slightly increased with, not here, sorry. So this slightly increased with the increase in the concentration of the aluminium, and yeah, this one is the magnetic property, how the magnetic property is varying with the substitution of this aluminium. Definitely this with the substitution of this aluminium, magnetic property is going to be changed with the titanium. We are trying to search what is the reason behind that, why the magnetic property is going to change with respect to substitution with aluminium. So we extend this study two way. One, we are going to first we are going to anneal this system, because you can find there is a drastic variation in the magnetic property if we replace this titanium totally with the aluminium. So definitely there is a change in some magnetic interactions are going to be occur, due to which this drastic deterioration in the magnetic property is observed. So further, in order to understand what is the reason behind this, we take the sample for some advanced characterization. We did some VBS spectra, as well as we go with this particular sample for the XM3D measurement, and we found this. If we go with the VBS spectra, you can see that after annealing, yeah, there is a result like that. If we anneal this sample, the two things, the form BCC phase is become major. The initial CC phase is the secondary, you can say minor, and after annealing the minor BCC phase is going to be major. As I told, since this system having solid solution phase, if we are annealing this with getting some energy, there is a rearrangement of atom after at the local region. So this type of penetrating phase formation may occur in such system. And further, the value of magnetization, as you can see, around just going to be double, around 50 to 110 approx. So only with the annealing. So definitely with the annealing, there is something due to which the magnetic interactions are going to be changed. So in order to understand this, we go with the VBS spectra, and we found these are the, you can say the VBS spectra is recorded at binding energy of 40 electron volt, and then we can see there is a 4 or 5 different features. There is a, you can see 8 different features in these two spectra, and the major thing is occurred due to the change in the peak intensity at the zero Kelvin. So definitely there is a change in the, you can say, density of a state occurs for the Fermi level. So we further understand which type of particular element is going to be responsible for this, what are the changes occurred at the zero Kelvin. So you can see we found resonance for the iron, and you can say ABCDE feature for iron is more dominant. So we can see that after annealing, this iron and nickels are going to be more dominant as compared to the other element. So before that, you can see the feature, these the magnetization due to these components are weaker. However, after annealing, due to change in the structure of local arrangement, this particular you can say at 0 Kelvin, these particular elements are going to be more active. So if we see this access, and further we did this access and XMCD measurement. These measurements are synchrotron based system. These are performed at ARACAT WIM 920. So these are the access spectra, and this access spectra is against there is a two thing. One is that this iron, cobalt, and nickel existing in the metallic nature. However, definitely there is a certain amount of iron and chromium is become oxidized, but with when we are going to calculate that, since we are annealing, there is a chance surface of these particular alloys are going to be somehow oxidized. So we are going to neglect this the oxide that area, whatever that area of the oxide cations, we can neglect it in the calculation of the magnetic moments of that particular individual element. So we calculate magnetic moment by using this sum rule, and we found these are the two in this table we can see the asynthesized state we follow. So you can see in asynthesized state the magnetic moment of these particular iron, cobalt, nickel are somewhat 0.127, 0.067 and 0.026 for the iron. However, in this annealed sample, there is a drastic change in the magnetic moment of this iron and nickel. So the orbital and spin magnetic moment, total magnetic moment of this particular system is totally enhanced up to the 2 or 3 times when we anneal this system. So with this, we again, as I told you, there is a major problem with this type of system is that resistivity for conventional system. So this particular system having almost resistivity double to the conventional system. So there is a large scope. If we tune the system and optimize the system, this particular system may replace the conventional salt magnet for industrial applications. So with this, these particular systems are having some benefit, and definitely we must have to optimize composition for the proper property. And since these are the multi-component system, we can obtain multifunctional property in this system and easily tune properties of a particular alloy is going to be having multiple different functional property, and that will be the beneficial for the industrial application. So these are my collaborator, and these are my group. Presently 4 PhD students are working. Out of these 2 are working in the magnetic material, 2 are working in some energy storage materials. So for more detail you can follow this our website, and thank you. These are the funding agency that support the research.
Thank you very much for talking. Time for questions.
Yeah.
First of all, very nice talk, Dr. Sai. Could you explain about this XMCD data after post-annealing? It gets enhanced, it seems. So could you explain the...
Yeah, actually this XMCD is, as we are knowing, as I told, if there is a change, yeah, you can go this. So since as synthesized state, we have this FCC is a measurable. After annealing, there is a rearrangement of atom due to which this FCC state is transformed to the anisotropic BCC phase. So that rearrangement like thing is going to be occur, and this rearrangement is maybe somehow responsible for this iron like feature is going to be occur. The structure is somewhat BCC structure of the iron. So you can think like that, and in XMCD as well as this BBS spectrum, we found that iron feature is going to be pronounced. So that interaction is somewhat like that occurring similar to the case of the iron, due to where the magnetization is going to be just double from 55 to 110.
Okay, what was the sample size for XMCD, for being XMCD?
Yeah, 10 mm pellet is sufficient.
10 mm pellet.
So sometimes it may create a problem with that since these are highly magnetic materials, so stuck it and stuck with the magnet, external magnet and all this. So we are using this 10 mm as thick as possible pellet, 10 mm mount dia.
Okay, thank you. Yeah, very nice talk.
Thank you.
So I have a question regarding this. You are showing this atomic scale and these AD value. So did you do fulfill refinement, or this is just one?
Actually, we don't have any JCP-based data of this system because this was a totally new system. So we are going to fit it to the Levine refinement. We are going to fit it proper for the refinement.
So I have a question because few of your data, this XRD data itself is showing some kind of structure, background structure.
Yeah.
So what is the reason for those? I mean, you are showing some different.
Yeah,
kinds.
this one, yeah.
Now, earlier also, I can say like parabolic things.
Yeah, in some cases, yes. In definitely.
Bottom one, you see.
Yeah. So this one is due to the this one is a synthesized state. Somehow there is a different you can say the different particle sizes there. So this one is a hand-picked sample only. So we take different. There is a range of the particle of the procured sample. So that procured sample, if we are going to smooth in it, so there is some. You can say some particles are bulk like thing, due to that maybe that will be.
Usually such kind of background comes from the diffuse scattering. Okay. So diffuse scattering.
That is also one of the reasons, because if we have a curved surface, having particle like that, there is a not homogeneous distribution at the surface of the particle. Since we take procure the metal particle, and these metal particles having different sizes, and we are not going to press it because the titanium is very hard. So whenever we are going to make it powder by hand, it is impossible to process make it very smooth and become the surface is going to be that smoother one, so that we will. I think like that. Maybe.
First time I saw XRD.
So
neutrality is usual.
Yeah.
Neutron you can get the opposite diffuse scattering because there are fluctuation and other things you can.
So actually, I think this one is only because of that the surface is not smooth at hand mixed state. This one is hand mixed state. And if we ball mill it, then this one is going to be flatter. Because after milling, the particles are going to be homogenized. Size is going to be homogenized. That will be the one of the reasons.
Okay, thanks again. That was very nice talk.
फोटो कोई खींच नहीं रहा है इन लोगों को सब बोलना पड़ेगा
Yeah. Thank you. Thank you very much.
Okay, so with this we close the session.
Thank you to the chairperson for a nice conducting session, and time to tea, and tea is waiting for the outside, so we have to move.